there are many different kinds of designs for how to actually perform an experiment. And each of these designs then allow you to collect the data in a certain way, and then you use ANOVA methods to actually analyze the data. We're going to talk about the most simple of these designs first, and it's called a completely randomized design, or CRD for short. And its name simply comes from, let me get my red pen out here. Oops. There we go. Now we have my red pen. This name simply comes from the fact that treatments, or in other words for us, factor levels, are completely randomized when assigned to an experimental unit. In other words, let's say I have 100 different experimental units that we're going to actually take measurements on. Now, what we would do then is, let's say, randomly select 10 of these experimental units and say, okay, that's going to get factor level 1 or treatment 1. Randomly select another 10 units or experimental units and say, okay, those 10 are going to get treatment or factor level 2, and so on. And so the key is, though, this random selection of experimental units to get a treatment or factor level. Let's relate this now to the Wheaties cereal example. So what I could do is I have 10 experimental units, which would be stores in our particular case. And what I could do is, let's say, get slips of paper where I write a particular store number down on each slip of paper. Then I put these slips of paper into my hat, shake it up really, really good, and then without looking into the hat, I randomly select number 5. And so what this then can mean then is that let's say the first treatment level, which is, let's say, design type 1 for these Wheaties boxes, is going to go to store number 5. Then I shake my hat up again, put my hand in, don't look. Oops. And now store number 7 is also going to get treatment number 1. We'll do this one more time just to emphasize the point. And this time now, store number 3 is going to get treatment or factor level 2. In other words, the second type of design for these Wheaties boxes. And I could do that for all 10 of these stores, which are experimental units, so that I can assign treatment to experimental unit. So you can see this is essentially done at random. And the reason why you want to do that is to avoid any kind of biases that might be presented by saying, hey, maybe this particular kind of store is going to get this kind of Wheaties box. This particular store gets this Wheaties box, which could then bias your results in the end. Now, I do note for this particular example here with Wheaties boxes, there's no particular reason why I only have 2 stores for design 1, 3 stores for design 2, and so on. I just purposely chose an uneven number there to emphasize that you could have uneven numbers for each, in this case, design type. But in an actual real-life setting here, does it make sense to say some treatments will have an uneven number of experimental units compared to other treatments? And the answer is no. But maybe for particular reasons, it might end up happening. Okay, so obviously I use a hat with numbers in the hat to make this random assignment. But, again, in a real-life setting, you wouldn't do that. Instead, you use a computer to help you do that. And so one thing I would like you to think about is, well, how could we actually make this type of assignment in R? Think about it some. You can remove the blacked out area of my lecture notes and you can find what the answer is. It actually uses a function R that we've used before. Okay, now, so that was with respect to the Wheaties example. We've also talked about another example with respect to allergy medications, about which one relieves allergy symptoms the best. And so a pharmaceutical company would actually do a clinical trial to determine this. And so what these pharmaceutical companies will do is that they'll recruit patients that they can then experiment on, you could say, to determine, well, which allergy medication is the best on average. And to do this in a way that's not biased at all, what they would do is assign individual patients or people to a particular allergy medication, which would be our factor levels. And so perhaps, let's say, patient number 4, 8, and 9 each get Seldane. Patient 2, 1, 5 each get Allegra, and so on. The key is that this assignment is made in a random manner. Okay. So now remember, the overall goal with ANOVA is to determine if population means for the factor levels are different. And so to do that, to begin with, then we perform this kind of a hypothesis test, where the null hypothesis is that all the treatment means, meaning the T treatment means, the T factor level means, are all equal to one another in terms of the populations that they represent, where the alternative hypothesis is that at least 2 of the means are unequal. Now, to do this hypothesis test, we can use a test statistic, and we've already seen a little bit about that, and we're going to use this test statistic called F sub obs. With a test statistic, as you might expect, we can use a p-value as well, because we're going to relate this all to the F distribution. Now, to do this hypothesis test, though, we cannot use the confidence interval method, and that's because we're looking at more than one. We're looking at too many means here. We can't just find one confidence interval for, let's say, T different means. But confidence intervals will play an important role later on in another subsection of our notes. In particular, when you actually, let's say, reject HO, so you're saying, hey, at least 2 of the means are unequal. Well, you want to find out which of those means are unequal. And that's where confidence intervals play a very, very important role. Okay, so let's walk through the steps of this hypothesis test. For the test statistic method, we state our hypotheses. Step 2, we state our test statistic, which we've seen before, which is the ratio of MST, mean square for treatment, divided by MSE, which is mean square for error. Then we compare it to a critical value that ends up coming from the F distribution. Note that there's only one critical value here. It's F and then alpha in the subscript, which means that the area, let me actually draw it out. So maybe this is what the F distribution looks like. We have alpha there, we have 1 minus alpha there, and here's what our critical value looks like. So it is the 1 minus alpha quantile from an F distribution. Now you probably notice here that I've drawn the critical value on the right side of the distribution, because typically we will use low values of alpha, like alpha 0.05. And this is going to be essentially our borderline, where we can say if we're greater than that, then this F obs that we've observed is unusual if the null hypothesis is true. Again, this just relies on what we've learned in the past about hypothesis testing. And so if F obs is greater than that critical value, now we're saying, oh, hey, this is very unusual to get this kind of a value, so therefore our null hypothesis actually must be incorrect. So if you also notice here, notice where I'm only going to be on one side of the distribution. And the reason why can kind of be seen by that Excel spreadsheet demonstration that we had with the Wheaties example. And that was, as the means got more different, F obs kept on going up, up, and up. And the lower the F obs was, the more alike our means were, in terms of our sample means, that is. And so that gives you some intuitive feel then for why this is essentially is only a right-tailed test for this particular situation. The only way that you will, the only thing that's going to happen to F obs if the means are different is that the actual F obs is going to go up. So large F obs values indicate evidence against equality of population means. Now, in terms of this critical value, we have T minus 1 degrees of freedom is at first degrees of freedom. And again, we often equate that to a numerator degrees of freedom. And in fact, that ends up being, you would see this in MST. It's actually the denominator of MST itself. And then the second degrees of freedom is going to be that your total sample size, which is we're going to call capital N. And we're going to subtract off then the number of treatments or factor levels that we're looking at. This is often referred to as the denominator degrees of freedom because it's associated with MSE. So, test statistics greater than the critical value. If that happens, we reject HO. Otherwise, don't. And then step 5, state your conclusion in terms of what this means now that we reject HO. If we reject HO, there is at least one pair of means that are different. But if we don't reject HO, well, there is not sufficient evidence to conclude that any of the population means are different. The key, though, is that when you do this phrasing here, you can use this as a template, but change certain elements of this template relative to the problem that we're investigating, like, for example, with the Wheaties cereals. Okay, so with the p-value method, state your hypotheses, find your p-value, and again, what we're going to be looking at is how extreme is this f-obs relative to an f distribution. So in other words, the probability that a random variable x with an f distribution is greater than what we actually observe for this test statistic. Step 3, state your alpha. Step 4, decide if you reject or don't reject, just like what we've done in the past. And step 5, state your conclusion. Now, unfortunately, there are actually some mathematical assumptions that go into all this in terms of why we can use an F distribution here. Here are the assumptions. The populations for each treatment have an approximate normal distribution. The population variances for each treatment are equal. So what this means then is that, let's say, y sub ij has an approximate normal distribution to it, where across the different treatments, the variances are the same. Without these assumptions holding, type 1 error rates could be higher or lower than what's actually stated in a hypothesis. If I state alpha 0.05, the true value actually might be something different. But fortunately, very fortunately, small to moderate violations of these assumptions, that they're okay. The ANOVA methods will still work well, meaning that if I say my type 1 error rate's 0.05, if I have, let's say, a small violation of some of these assumptions here, my true type 1 error rate is probably something very close to it. Now, what can you do, though, if you are worried about these assumptions? Here are some options. One can use what's called a non-parametric method to test equality of population means as well. And what a non-parametric method is, we need to first think about what a parametric method is. It's just a term that statisticians use to say what we're doing here is a parametric method because we have some probability distributions of assumptions behind all this. A non-parametric method doesn't have these assumptions. You might be thinking, well, why don't we just use the non-parametric method then? Well, the non-parametric method might not be as powerful as the parametric method, depending upon the circumstances. Also, instead, we could use a different distributional assumption instead. And if you want to know more about that, a great place to start is to take a categorical data analysis class from me, where we look at situations where, let's say, y sub ij might be binary, or maybe y sub ij might be, let's say, a count response. How else could we actually analyze the data if we knew that? And so we spent a lot of time talking about that in our course. So why are we using these ANOVA methods that I've been presenting to you now, given the potential assumption problems? Well, we got to start somewhere. This is an introductory statistics course. The methods that we are talking about here work well in many different situations. And we just need to start somewhere. If you find this stuff interesting, take some more stat courses. There's often whole semesters on non-parametric statistics that one could actually take. Those courses can allow you to see more about how to approach the problem in a different way if needed. Also, it's important to note that if, let's say, we have just 2 treatments, then essentially what we're doing here is essentially equivalent to what we were doing earlier in the semester when we were looking at, let's say, a hypothesis of mu1 is equal to mu2 versus mu1 does not equal mu2. Okay. Now, when one uses ANOVA methods, one often summarizes all the calculations that are made using what's called an ANOVA table. Here's what one looks like. So in the first column here, we have the word source. What that basically means is what is the source of variability that we have in our observed information that we're seeing in terms of the y sub I j's. And we have 3 different sources. The variability could be associated due to the treatments themselves. And remember how we calculated one measure of variability called SST, sum of squares for treatment. Another source could be due to what's referred to as error. And this is associated with then SSE, sum of squared errors. Where if you remember for that particular quantity, what we did was we took each of our observed values and we subtracted off from the corresponding treatment or factor level sample mean. And so we're looking at how far are we off from that treatment mean. And so that's the second source of variation. And the third source of variation is, I guess you could say, well, maybe I shouldn't say that there's 3 sources of variation. There's actually 2 sources of variation, excuse me. And what the third row, though, of this table represents is what's called the total variation. In other words, let's simply sum up these 2 sources of variation, and we get what we've seen before as the total sums of squares, where we take each observation and we subtract off the overall mean from all our data. Okay, so we have a source column, we have an SS column for sums of squares. Then if you remember, we also have discussed mean squares as well. And so we have a mean square for treatment, a mean square for error. We have a corresponding degrees of freedom, or DF, associated with these quantities that we've seen too. Remember that now that this capital N represents our overall sample size. And then we also are going to have a column called F. And this F is going to have our F obs in it. In other words, again, MST divided by MSTE. Now you might be wondering, hey, Chris, you got all these empty cells in the table. Why aren't you putting anything there? Well, this is just the standard way that we typically write the table. If we do, let's say, take TSS divided by N minus 1 and put it there, it doesn't really give us any meaningful information. So that's why you don't see those cells of an ANOVA table filled. So on page 7 of the notes, I just give you a reminder of what these quantities represent that we've seen previously. Let's go ahead and go into our example with the Wheaties cereal example. We've calculated all these quantities before, so you can look back earlier in our course notes. And you can say fill in the blanks or fill in what those table cells would be. And so that's what I actually did here. I don't think it would be worthwhile for me to bring up those previous notes to do that. Please look back on your own. The most important thing, though, of this part of the example, though, is how can we have R automatically perform these calculations for us? Here's how. We can use a function called AOV for analysis of variance. You might be wondering, why isn't it called ANOVA? Well, you'll see later. There's actually another way that we can get this table too, and it does actually use a function called ANOVA. But this first function that we're going to look at is called AOV. And what we can do with this function is that we have an argument called formula. We've seen formula arguments before, for example, with the aggregate function. And what we can do is take our response variable, y sub I, j, and basically what we're going to say is that, excuse me, this y sub I, j can, let's say, potentially change or as a function of the actual serial design type, serial box design type. And so that's why I have design on the right side of this tilde. And then we need to put data equal Wheaties. And if we use the summary function with the end result, which we put in mod.fit, then we get our ANOVA table that we just saw above. Notice we also get a nice little p-value to do our hypothesis test as well. Now you might be wondering here, let me do some erasing too. Why am I using factor here? Oops. So factor is an actual function itself in R. And what this factor is going to do is going to tell R, hey, I have these design types, which are simply denoted by 1, 2, 3, and 4. R, please treat these as actual factor levels, rather than, let's say, thinking of factor level 4 being greater than factor level 1, because it's actually written as a numerical value. So again, what this factor function is doing is telling R to basically treat this coding for the design types as, you could say, like a categorical or qualitative set of levels. 1, 2, 3, and 4, where 3 is not greater than 1, 2 is not less than 4, and so on. That's why I have it there. Now, if instead, let's say in my data frame, let's say I had 1 coded as the letter A, 2 coded as the letter B, and so on. So I use an alphabetic coding there. If I would have done that, I would not have needed the factor function there. The factor function is just for the fact that I use this numerical coding. I need R to think of it as a factor level, a qualitative level. Okay. Now, I put the results from AOV into mod.fit. And in R's terminology, this mod.fit actually ends up being a list type of object. So there's a whole bunch of information stored in there. And if I want to see exactly what's stored in there, I can use the names function. And you can see when I do that, indeed, I do have a whole bunch of information. We won't talk about that information right now. We'll start talking about that later in these notes. Okay, so let's do our hypothesis test then. Step 1, state your hypothesis. Step 2, state your test statistics, so we can go to the output and get 11.22. Step 3, state your critical value. What we can do is use the QF function, quantile F distribution, where I want the 90.95 quantile. Suppose alpha is 0.05 in this case. I take my degrees of freedom, and let me go ahead and jump on over here to R, excuse me. So I've already read in my data. And just to make things easy, I set my T value, which is the number of treatments or factor levels. I also set my number of observations I have to be 10. And so if I combine that then with the QF function, where I put the degrees of freedom, I write it in there correctly. Note that I could have put this there as well. Remember, DF1 corresponds to the numerator degrees of freedom. DF2 is the denominator degrees of freedom in this kind of a situation. And so my critical value is 4.75. And here's the actual code again that we just saw, but now inside of 10 itself. Let me go ahead and do summary. And so you can also see here the corresponding degrees of freedom that we would need as well when we use the QF function. Okay, let me jump back here. Okay, so test statistic is greater than critical value, reject, HO. What does this mean in terms of the original problem? Well, there's at least one pair of these design types for these serial boxes. At least one pair of these means that are different. So consequences then. Well, some design types are better than others in an average sense. Thus, the company would make more money, meaning because they would be selling more boxes with maybe using 1, 2, or 3 of design types than they would with the remaining design types. And in terms of the company's perspective, of course, they want to know, well, which of these design types then is best on an average basis for the sales? Well, we shall soon see. So stay tuned. Now, all this ANOVA stuff that we've been doing actually corresponds to, or you can phrase it in terms of a statistical linear model. What I mean by the word model is that my response variable, y sub ij, so the I corresponds to the treatment or factor level, like the design type. The j corresponds to the actual experimental unit within a design type, so like a particular store within a design type. This y sub ij can be written in a mathematical way that tells me how these y sub ij's actually come about. And so what you might expect on this right-hand side of the equation, it's going to have to do something with the factor level. Based upon the factor level, that's going to control how this y sub ij comes about. But also we know that there might be other stuff that affects how many boxes are actually sold, if we think of the Wheaties example. So perhaps, I have some extra stuff there. How about we just call it error? So I'm going to take the factor level, information about the factor level, plus error. This is my model. So if I somehow knew all this information, I could actually come up with the actual y sub ij. And so there's actually 2 different ways that you can write out an ANOVA model. We're going to actually jump to the second way first, so I think it's a little bit easier to see. And we're going to use what's called a mean effects model. And this is what it looks like. So my statistical model says that each of the y sub ij's, in terms of like the number of cereal boxes sold, come about the following way, where I take the mean, the population mean for a particular factor level or the particular design type, and then I add to it a random error term that helps me account for everything else that could affect sales of a cereal box, other than the actual box itself. So in other words, let's look at y sub 1, 1. We're going to relate it to the Wheaties example. So y sub 1, 1 means that for design type 1, store number 1, this is the number of boxes sold. And the way that this comes about through this model is that if I somehow knew what the population mean was for all the cereal boxes, excuse me, for all the stores when this design type would be used, this mu sub 1, y11 is equal to mu sub 1 plus, and there's probably going to be other stuff that's going to affect the sales as well, such as maybe for some reason the store had to close for a day because there was a water leak, or maybe that it was storming outside for a number of days during the month, so people couldn't get to the store as often, and so that drove the sales down. Or perhaps maybe the store was running a big sales promotion, not necessarily for Wheaties, but for something else, and so that drove a lot of people into the store. If there's a lot of people in the store, maybe more Wheaties boxes were being sold. And so what this epsilon, so this is a Greek letter epsilon, basically says is, here's everything else that could affect the sales of these cereal boxes other than the actual design type. Now the problem is, of course, we might not know what is actually also affecting the sales. We don't know everything else. So this is why it's called a random error term. And what we're going to do is we're going to say that each of these random error terms has a normal distribution to it, where on average the error is 0. Okay, And it's going to have a particular variance, which we're going to call sigma squared. And we'll put a little epsilon on it to help us know that this is a variance dealing with the epsilons. So if we somehow could observe what this random error term was, and if somehow we could actually get at this parameter value here for the mean sales, we would have y sub 1, 1 exactly. And we could go on to, let's say, design type 1, store number 2 with that design type, and we could write it out again like this. And we could write it out all throughout all 10 stores that we have. And so again, and sorry I'm repeating myself here, but it's an important point. What we have is a model, a way that we think that the sales for these cereal boxes actually come about. And now notice then, when we create a model like this, look what happens. What would happen if mu1 is equal to mu2 is equal to mu3 is equal to mu4? Sorry, I'm writing over my text there. In terms of the design type, the cereals here. What would happen to this model? Now, all these means would be exactly the same. And what we're left with is just simply the leftover random error term. That's it. Okay? So, mean affects model. So we're looking at how the mean affects the response. Now, another model is what's called the treatment effects model. And it's exactly the same as what we just saw, except for where we had a mu sub I. Oops. Now we have mu plus alpha sub I. Both mu and alpha sub I are parameters. We will want to estimate them. I'll show you how to do that shortly. And what mu is let's say an overall mean. So related to the cereal example, perhaps it's the overall mean that you would have for any store, no matter what design type you would have. And then we take into account that, well, if I use a different design type, I might have a different y sub ij. So this alpha sub I then represents, let's say, the treatment effect. How will the design type affect y sub ij? And so basically what it is how it could be positive, it could be negative, and it adjusts that overall mean by some quantity, some numerical value, so that we can get at what the response is. And so it's just a different way to look at a model like this. Both the treatment effects models and mean effects models are widely used whenever one's doing experimental design, whenever one's doing ANOVA methods. Okay, so let's look at that treatment effects model in more detail with respect to the Wheaties example. How can we find these parameter estimates? And so, if you remember, the mean number of boxes sold for design type 1 was 15. For design type 2 was 13, and so on. And what our treatment effects model says is that how the actual number of boxes sold per store come about is through this particular model. And so what I've done is that I've written it out in terms of, we have I equal 1, I equal 2, and so on for design 1, design 2, and so on. So this is how we're saying that this actually comes about. So because of that, then, we can now try to find parameter estimates. In other words, our observed value of our statistics using the information that we have available from our sample. Here's how it's done. So this mu plus alpha 1 is representing basically what happens with design type 1 when it's being applied. So what we could do is we could set then that mean value that we got for design 1, which was 15. How about we set that equal to mu plus alpha 1? That seems like a reasonable thing, because what we get in our sample is going to try to estimate these population parameters. And since now we're talking about estimates of these parameters, our statistics, I'm going to put little hats with like you can see, like, think of it like the caret symbol. In statistics, we refer to them as hats. I'm going to put hats on top of my parameters. So I have mu hat. I have alpha hat 1. And I'm going to set mu hat plus alpha hat 1 to be 15. I'm going to do the same thing for design 2, design 3, and design 4. So now I have a system of equations where I have some unknowns, mu hat and these alpha hats. And what you learned in an algebra class is that when you have a system of equations with some unknowns, you can try to solve for the unknowns. And that's what we're going to do. But we have, unfortunately, one little complicating aspect to it. We have 5 unknowns here. Mu plus then the 4 alphas. So we have 5 unknowns. And we only have 4 equations. What you learned in an algebra class is that, you have an infinite number of possibilities than what these 5 unknowns would be. So what can we do? Because I still want these estimates. Well, how about we make one of these unknowns known? We're going to let alpha hat 1 be equal to 0. I could have used alpha hat 2 to be 0. I could have used alpha hat 3 to be 0, and so on. I'm going to choose alpha hat 1 to be equal to 0. I'll explain a little bit more why later on. And the reason why I am actually doing this here is because this is what R is going to do. So if alpha hat 1 is equal to 0, then that means that mu hat has to be 15. So again, let me erase it because it's getting messy. So if this is gone, then mu hat has to be 15. And now it's just a matter of doing algebra to solve for the other alpha hats. Okay. Now you might be wondering, okay, you're saying that then design type 1 has an alpha hat of 0. Isn't that going to cause problems in your analysis? And the answer is actually no. What we're essentially doing by setting alpha hat 1 to be 0 is that now the meaning of alpha hat has actually changed a little bit. Now we're measuring how we are deviating. I'm sorry, let me restate that. Now, for example, alpha hat 2 is a measurement of how design type 2 is different from design 1. Alpha hat 3 is now a measurement of how design type 3 is different from design type 1. That's what these alpha hats now are going to represent in terms of our model. In the end, though, it's not going to change our analysis at all in terms of our conclusions, because no matter what I chose as an alpha to be equal to 0, we're still going to have the same system of equations. So the overall estimated mean effect, let's say for design 1, is still 15. For design 2, it's still going to be 13. So in the end, it's not going to actually affect our analysis. It's just a way for us to get these parameter estimates, and always in the back of our mind, we need to think about, okay, this is what alpha hat 2 now actually represents. Now, there are other ways that you could take care of this problem of 5 unknowns with 4 equations. So, for example, some of you might run into a statistical software package called SAS. This used to be for a very long time the top statistical software package out there. That's no longer true. But the way that SAS would use it, and lots of people still use SAS, the way that SAS would approach this problem, it would say, okay, let's let the last treatment level 4, design type 4, we're going to set that alpha to be 0. Where what R does is sets the first treatment level always, in terms of some kind of ordering of the treatment levels. It's always going to set the first one to be equal to 0. So if we had, let's say, treatment levels A, B, C, and D, R would set the A level to be 0 for that alpha. SAS would set the D level to be 0. Okay. There are other ways to do this too, not as much anymore, but what used to occur is that one could, let's say, set the sum of all these alphas, that sum equal to 0, and you could still then come up with the parameter estimates. But in the end, it's still not going to change the overall final analysis. So what role then does epsilon sub ij play? Because notice we didn't include that. Well, epsilon sub ij is actually a random variable. It's not a parameter itself, so that's why we're not estimating it. Do note that the sigma squared epsilon, that is the variance of epsilon sub ij, is actually a parameter. And the way that that is actually typically estimated is actually with mean square error. Okay. Now, epsilon sub ij is assumed to have a normal distribution to it. And while we're not going to explore it in this particular class, if you took more classes in this area, you would. You should think about, well, maybe we could somehow look at that assumption with our observed data to see if our observed data kind of satisfy what this underlying mathematical assumption is. And so on your own, I'd like you to think about that. How could we actually look at that assumption with our observed data? And you're going to see some of that. You'll get another, how should I say, you'll get more information about how to actually kind of do that once we talk about models called regression models too. Speaking of regression models, what we're going to do is look at a different way that we could come up with these parameter estimates that's based upon this concept of what's called a regression model. Now, another way that we could have, instead of using the AOV function, another way that we could have done all these calculations is to use a function called LM. LM stands for linear model. What we basically have here with ANOVA is what's called a linear model. We have a model, we've talked about that, but it's linear in the sense of, notice how we're taking like a mu plus epsilon sub ij, or mu plus alpha sub I. And using the same syntax as what we saw with formula, I put my response in general, that's my y sub ij, and then I put information about my factor levels on the right side. I put in my data. I then run the LM function. I put the results into an object called mod.fit.lm, for the lack of a better name. Why am I using mod.fit? Model fit. We're basically, let's say, fitting a model to data. LM then is just going to correspond to that function name there. But I could use a different name. And then what's returned is a list type of object in R's terminology. If I use names with that, then we have information about what's actually stored inside there. In particular, what I want to look at is this right here, coefficients. And so to actually access that bit of information, I put my list, $, the name of the component of that list that I want to take out of it. And what we get here is actually our parameter estimates. Here's mu hat. Here's alpha hat 1, alpha hat 2, oh, I'm sorry, that's alpha hat 2, alpha hat 3, and alpha hat 4. So just to come back here, this is located on page 14 of the notes. Okay, excuse me. So the reason why I'm showing you this, first of all, is to show that indeed you can come up with these parameter estimates by using this function. And if I did a summary of all the components inside that list, we get some output here. And what we see here, we have a column called estimates. And then we have information about, okay, what R calls the intercept. That's our mu. If you think of it in terms of just a regular old equation that you would have in an algebra class, A is here is our intercept. And basically that's the role that mu is playing with our treatment effects model. And then we also have our other parameters. We have some descriptions corresponding to our other parameters that we're trying to get. Then we have a whole bunch of other stuff in this table that for us in this particular class is not going to be meaningful. But real briefly, it's worthwhile just to briefly mention this. And that is, so we have a column called std.error that corresponds to standard error. And what this actually means is this. So for that 1.958, that's equal to the square root of the estimated variance of mu hat. So mu hat is a statistic. If we think of it, before we actually come up with an estimate, it's a random variable. If it's a random variable, it can have a variance associated with it. And if I put a hat on top of that var for variance, that means the estimated variance of mu hat. If I take the square root of it, I get a standard deviation, or what people like to, of course, change names there. They call it standard error. Okay? And then we could do some kind of hypothesis test corresponding to the particular parameter. Is that parameter equal to 0 or not? And so what the t-value column actually gives us is a t-test statistic to do that test. And then the last column here is then a corresponding p-value with that test. Again, we're not going to bother with that in our particular course. We will see it a little bit later where it will actually be important to us. But for now, for what we're doing here, it's not important. We also have some other information here too. So for example, this thing called residual standard error, that's just another way that people like to use to represent the square root of MSE. And what this is going to then be, you could say, is sigma hat squared epsilon. It's an estimate of that variance, I'm sorry, now the standard deviation of that random error term. We also have an F statistic here. That should look familiar, 11.22. The degrees of freedom should look familiar. And guess what? There's that p-value that we've seen earlier too. Now, if we take this mod.fit.lm list object and use a function called ANOVA with it, now we get this nice organization or this nice table that we would like to work with. We get our ANOVA table. So it's just the same way to do what we did with the AOV function. It does take a little bit more effort, not much more, but a little bit more effort. And the reason why I'm actually showing this, because you might be thinking, why don't I just show you the easiest way? The reason why I'm showing you this is as follows. Both of these AOV LM functions are typically used in actual practice. Okay? But this is really the big one. And that is a problem that some students have is relating an ANOVA model to a regression model. We will go into regression models in detail shortly. But all that an ANOVA model is a special case of a regression model that we will see later. And I put this here now so that eventually we're going to actually come back to this place in the notes and see why indeed an ANOVA model is a special case of a regression model. Students often have difficulty with that concept to understand it, but it's an important thing to do, that all this essentially is being encompassed in one overall grand way of, let's say, doing modeling. So that then concludes this section on the completely randomized design, how we can then analyze the corresponding data using ANOVA methods.